And so what we're going to talk about today is about organizing categorical data, okay? And it should be easier than organizing quantitative data. And you've probably been doing that many times, right? When you have categorical data, for instance, that student data, have 22 pieces of data, have gender variable, okay? And I want to sort out this gender variable. I will, again, just like dealing with quantitative variable, I made a frequency distribution table. In the frequency distribution table, I have the same kind of information. First column is the class. Now, in this time, class will be each of those categories in your variable. And for gender variable, I only have two different classes, right? I mean, two different categories, female and male. And then I can start counting frequency of occurrence for each of the categories, right? I have 9 and 13. And then each of these numbers I divide by total, I get the percentage or relative frequency, okay? Then I can convert it to either bar chart. Over here, I actually use a relative frequency. This is a percentage. I use relative frequency to make my bar chart. Okay, so for female, it's about 40%, and for male, it's about 60% in that class. Okay, I can make a pie chart. Just draw a circle, right, and then divide it into two pieces. Okay, one piece take on about 40%, the other 60%, and it can be done accurately and easily by SPSS. Okay, by any software, in fact. And I think you can do it by hand without problem. Right, so make sure you do this on that exercise. And I wonder if you have seen this before. This is also a bar chart, okay? But we call it Pareto chart. It's actually a bar chart, but the arrangement of these bars, it is according to their frequency. So you sort out the frequency, right? The highest go first, and next higher frequency, and then next higher, and so forth. So it's easier for us to see which one have a higher frequency, which one have lower frequency. And the chart like this is called Pareto chart. Okay. So organizing qualitative variable, it's pretty simple. I think you've done a lot. Okay. And you can invent your own charts as long as you display the information properly. That's good enough. Okay. Any question about this Pareto chart? It's used quite often, right? Especially have many categories. You like to do that. Okay, so that's another univariate analysis, right? So we done two univariate analyses, one for quantitative, one for qualitative, and both analysis we did almost the same thing. First, we organize information by constructing frequency distribution table. Then we convert it to chart. So you can see numbers, you can also see figure to see how the data spread. Okay. The variability pattern of the variable. Okay, that's a very important thing that we are doing in statistics. We like to understand the variability pattern. But oftentimes we do bivariate or multivariate analysis. We like to examine the correlation between variables. Okay, and so that's the next thing we want to look at. This first example is a bivariate analysis. Okay, and this is when you have two categorical variables. We can cross-tabulate the information and make a contingency table look like this. In this study, there's totally 100 individuals. Among them, some of them are smokers, some of them are non-smokers. In fact, 50 smokers and 50 non-smokers. Okay, we're observing whether they have cancer or no cancer. So there are 25 of them have cancer and 75 of them have no cancer. Right? So these two numbers should add up to 100. These two numbers on the margin also should add up to 100 because this is a column total, right? These two numbers are column total. These two numbers are row total. Okay, so that makes sense. And this gives us information about how this data is distributed according to these two variables, all right? The categories in these two variables jointly. This 20 is what? Number of people with cancer but are smoker. These are number of smokers who have no cancer. This is non-smoker that have cancer. This is non-smoker that have no cancer. Okay. By looking at this table, it also easier for us to understand the situation, the risk factor here is smoking. Is it hurting us? Is it, if you are a smoker, do we really have a higher risk of having cancer? In fact, you can look at these numbers and compute some statistic. Right? One statistic that people usually do in this type of study, this is called actually a retrospective study. Okay, at a certain time point, you saw some people have cancer and some people have no cancer, and then you're looking at whether they're smoking or not. right? They smoke or not. And this is called retrospective study. A lot of time when we're doing this type of study, people like to use this statistic called odds and odds ratio. The odds of smoker to have cancer is 20 versus 30. Okay? Actually, the odds is defined by ratio to chance. Chance of having cancer and chance of not having cancer. Of course, chance of having cancer, just by your common sense, right? We have totally 50 people. 20 of them have cancer. So if you're a smoker, this is the amount smoker. Okay? So if I say amount scope, what's the chance of having lung cancer? In this table, it says 20 out of 50, just by the sample. Okay? So the chance about 40%, right? And the chance of not having cancer is 30 out of 50, is about 60%. The odds is what? The chance of cancer versus not having cancer. So the ratio of these two. Of course, the denominator is the same, so sometimes we just use these numbers, 20 versus 30 as an odds, right? It's the same thing. So it's 6 over 9, 6 to 9. That's the odds of having cancer if you're a smoker. Okay? So what's the odds of not having cancer for not smoker? That'll be 5 to 45. Okay, a lot of times people also do the division, 5 divided by 45 to get an odds, which is a single number, 1/9. Okay, does it make sense? Right? That's how we define odds. But oftentimes people use this number called odds ratio, which is the ratio of these two odds. The odds of having cancer, right, for smoker is 6 to 9. The odds of having cancer for non-smoker is 1 to 9. What's the ratio of these two? Do the division, actually is 6. This 6 means what? The odds of smoker to have cancer is 6 times the odds of non-smoker to have cancer. Okay? And that tells us, well, if you do smoke, your odds is much higher than you do not smoke, all right, to get cancer. And that's an important statistic that people use very often, right, in evaluate the significance of a risk factor. Okay, and when you have your data created or organized in a contingency table, it's much easier for you to calculate these odds, all right, or odds ratio to get the result. Okay? In health profession, a lot of times you see this odds ratio statistic. Okay? Good. Now we can also convert this again to a chart. Okay? We call it cluster bar chart. Okay? We have one cluster and another cluster of bars. Over here, the red color is actually showing the distribution of smoker and non-smoker for people who have cancer. The green bar here shows the distribution of smoker and non-smoker for those who do not have cancer. And you see they're different, okay? For having cancer, the distribution of smoker and non-smoker, well, actually you have more smoker, right, for that group having cancer. For do not have cancer, we have less smoker, right, and more non-smoker, which means what? The distribution are not the same, okay? Having cancer and not having cancer, the distribution of smoking status are not the same, which means what? Having cancer and not having cancer significantly related to smoking or non-smoking. Okay, of course I can make the chart differently. I can make this red become smoking and then green become non-smoking and make these label having cancer along not having cancer, right? That's also called cluster bar chart. If you do it that way, still you can see the situation and can conclude it. If the shape, and over here the red bar, this is high, this is low. For green bar, this is low, this is high. So their distribution not quite the same, right, for these two categories. So we say there's a strong correlation. If this shape distribution, for this red and green are the same, right? For smoker, the green also higher for smoker also higher than non-smoker. That means what? There's really no significant difference among it. That means there's really no significant correlation there. Am I making sense? All right. The green bar distribution and red bar distribution, the shape doesn't look quite the same. That means there is a correlation, right? At different categories of outcome, risk factor, you're going to have different distribution of outcome. Okay. Yes.
They call this a cluster bar chart. What is the cluster on this one? Is it smoking or the cancer?
The smoking.
The smoking.
Yeah, the cluster. You can, as I said, you can do it differently, right? You can have this be the cancer, and then bar color as a smoking or non-smoking. That's fine too. Okay.
In this case, does cluster mean how they got the sample?
No. This does not relate to sampling.
Because
This just means that you have two cluster of bars there.
Oh,
Okay, that's it. Okay, it's different from sampling.
okay.
That's a good question though, but it's different. Okay, it's just because they have thin cluster together. It's called cluster bar. Okay, does it make sense? Right? I think you can play with it, right, on this exercise to understand or to learn a little bit more. Okay, so that's when you have two categorical variables. You can either make a contingency table or display it with this chart. This is very useful, the chart. Okay, but remember, now you have to be very careful when you look at this information contingency table. Okay, you see strong correlation. That sometimes doesn't really mean that this correlation is strong. There may be other confounding variable that's affecting this whole thing. Right? So the data, if it is from observational study, you have to consider or think about possible confounders. If they are from properly designed experiment, then the result will be easier for you to conclude quickly. Okay, good. Now, how about we have two quantitative variables? Now, how do we organize or study the quantitative variable, two quantitative variables and their correlation? The example I use here is the one variable is number of handgun register, and the other variable is number of people got killed by handguns. Okay. Now, is there a correlation between these two numbers? Number of people that have handguns and number of people got killed. Okay. Well, the people done some statistic. This is for a certain region. Okay, and they record this information. That is the number of handgun per thousand. The unit is per thousand. Okay, 1,000. So this is 447,000, and for these different years. Okay, at different years you have different number of handgun registered. Okay, and I'd like to see whether there's a correlation between number of handgun registered and number of people got killed. And how can I do that? Well, we can do a graph, so-called scatter plot. Each of these is a pair of number from a year. Okay, I consider this as x coordinate and this is y coordinate. I start plotting these points on the rectangular coordinate system. Okay, so if I do that, you're going to get a scatter plot like this. Okay, this first point 447, 13. 447 is x, 13 is y. You plot this point. Okay, the second order pair you can plot another point there, and just keep plotting these points. You get this so-called a scatter plot. Okay. From the scatter plot, you can see a trend if there is really a correlation, right? Here indicating that when the number of handgun registered get higher, the number of people got killed get higher. Right, so there's a strong correlation there. Okay, and that correlation is linear. Linear means what? That pattern is like a straight line pattern. Okay? Now, if you plot these points and you couldn't see a trend, that generally means there's really no significant correlation between them. Okay? But be careful, significant correlation doesn't imply cause and effect, right? Or relation, cause or relation, right? That doesn't mean that because there are more handgun registered, so there are more people got killed. All right, this is just telling you that there's strong correlation there. Maybe then you can use number of handgun register to predict number of people got killed. But doesn't mean that number of handgun register, really causes more people got killed. It could be that because there are more people got killed, so more people start getting handgun to protect themselves. Okay? Does it make sense? Strong pattern doesn't mean there's a strong correlation, unless your data collects through a properly designed study. Then you eliminate possible factor and really identify the right variable for examining the correlation. Then the outcome you may be able to draw the causal relation between the two. Okay? Good. Important. Now, what do we see from the scatter plot? Usually we like to see the form, right? Is there a straight line form, a curve, right? And also the direction. Is it going up as x go higher, y go higher? That means there is a positive correlation, right? When the x variable increase, y variable also increase. One variable increase value, the other variable tends to also increase accordingly. Okay. Also the strength of the relation. Now, if that straight line pattern, right, so clear, all the data points so clustered, so close together to a straight line pattern, that generally means there's a very strong correlation between the two. Okay. And also possible outliers. there may be errors. Okay, somebody may enter data wrong. You may have outstanding data, right? Or maybe there's significant, finding, right? The outlier is really a true data, but just at that range, this data value is so outstanding, right? So they might indicating a problem there too, right? Now, outlier doesn't mean error. Sometimes it is error. Sometimes it is very important message there. And then you have to investigate it, right? So every time you see an outlier, you don't drop it. You want to reinvestigate to see what happened, right? Maybe it is giving you a very important message, right? That the global warming is really, in very serious situation when you reach, at that pollution level, okay? So, so outliers, be careful. Outliers doesn't mean it's an error. Outliers sometimes means there's an important message there, okay? So be careful when you're interpreting outlier or dealing with outlier, okay? So let's look at these two charts, all right? Which one has indicating a strong correlation? Right or left? Right, okay. Your data point more closer, right? Stay more closer together, good. That's a strong linear trend, right? Now, if you have scatter plot like this, indicate positive or negative correlation? Positive, right? When one variable increase value, the other also increase accordingly. And that's a positive relation. Okay, if your data point goes like this, that's a negative correlation, right? Two variable goes different direction. When one variable's value get higher, the other value get lower. Okay, the other variable's value get lower. So that's negative correlation or negative relation. When you do have scatter plot look like this, you really cannot find a trend. That generally means there's very weak or even no correlation between the two. Okay. What about something like that? Is that indicating a strong correlation? Well, it's a strong correlation. There's a very clear pattern there. Okay? That trend is very clear. Now, if you use a software to try to calculate a statistical correlation, all right, and that correlation is linear correlation usually. Okay, and when you have a graph like this, that correlation number may be small. Right? Later on, we're going to talk about in the later part of the course. We're going to talk about it, all right, about correlation and calculate correlation coefficient. In this case, when you calculate that correlation coefficient, it may not be a significant number, may not be big. However, there's a curve relation there. Okay, this also indicates a strong correlation. As long as you see all those dots clustered so close together, and you see really a trend, a curve of a line, that generally means there's a strong correlation. Okay, so the correlation not always be straight line. It could be some kind of nonlinear pattern. Okay, great. This is another example of two quantitative variables in examining correlation in the same kind of result. Okay, this is about average temperature and mortality index from 22 countries. I lose the counts, right? Several countries. So we see a strong correlation. Average temperature and mortality index. Okay. This is a mortality index for a type of breast cancer in women, right? And in certain region of Europe. Okay. So that indicates there's a strong correlation. Does that mean that now we live in Ohio, we have higher, actually we have lower mortality index? That could be, okay? But you cannot say that the three temperatures causing people have higher, or country have higher mortality. Right? If you look at the geographic location for these countries, and very strangely, those countries that are in warmer temperature, a lot of them are underdeveloped than all these countries that live in higher latitude or colder temperature. Okay, so maybe the medical facilities and education, all these things are different. All right, people living in colder temperature, they just happen to have a better environment, okay, and better education, and they're doing better in almost everything. So their mortality index are lower. Okay, so temperature is really not the reason. Right, there are other things. But when you see a very clear trend, a lot of time people then can use that to fit in a mathematical model and start doing prediction. Okay, so there is a good reason to study the correlation. You say we cannot draw the causal relation, but we can use it to build a model. So eventually, we found that strong trend. We can use one of the variable to predict the other variable. Okay, and that technique is called regression. Right? We will learn it later on in this course. But at this point, we'd like to learn some graphical tool, right? Some descriptive statistic that can help us to quickly understand the situation. Right? And this is a very good tool, scatter plot, really good. Okay. If you have SPS, you can generate it so quickly once you have the data created. Okay, I'll show you how to do that. And this is the data that produced that chart. Again, we will just plot this versus this, each order pair, just keep putting dots on there, right? In this exercise, I think you can do that. I have one problem like that, right? Just plotting order pairs, reviewing your algebra, right? And making graphs on the rectangular coordinate system, okay? Any question? Does it make sense? Okay, good. And this is another chart that is in case I have a variable that is categorical and a variable is quantitative and want to examine the correlation. Okay, this case is I'm using that data. I have female and male student, and I want to see the distribution of heights for these two groups of people, right? So I make this so-called a side-by-side box plot. This box plot displays the spread of the heights for female student. This is for male student. This is the smallest number. This is the largest number for female. This is smallest, about 60-something. This is highest, about 75 for male. So it displays the range of the data and also give you some important statistics. In fact, this box, top of the box is the 75th percentile. The lower part of the box is indicating the 25th percentile. This line here indicating the median. That's how we make the box plot. Okay. Later on, we will talk about this again, and I will ask you to do some exercise in the class too, and practice this. Okay. But when you look at this chart, immediately you can see the male are generally taller than female, right? By looking at this so-called side-by-side box plot. Where is the categorical variable? The gender is a categorical variable. The height is quantitative. Usually, when you try to examine the correlation between these two, you will really want to compare that quantitative variable among each of these categories, right, in the categorical variable, right? So this is a nice chart for comparative study, right? Visualize the difference, okay? So you see, we done 3 bivariate analysis. When you have 2 categorical variable, what do? You do contingency table and make cluster bar chart, okay? When you have 2 quantitative variable, what do? Descriptively, you make scatter plot, see the trend. If you have 1 qualitative, 1 quantitative, this is a good one. Make a side-by-side box plot. You can see, right, the difference among them. Okay. If you try to make this chart and you feel like you find all these boxes about at the same range, that means what? There's really no strong correlation between that quantitative and qualitative variable. Each category, right, their spread for quantitative variable is about the same. Okay. So it's really, really good tools, right, for comparative study. Yes?
Did you say if you have 2 categorical, you use the cluster?
Yeah. If you have 2 categorical variable, you make that contingency table and you can do a cluster bar chart. There are actually other charts you can use, right? But the cluster bar chart is the basic one, right? But there are many statistical graphs that you can produce, right, for examine the correlation between 2 quantitative, 2 qualitative, right, or 1 quantitative, 1 qualitative. There are all kinds of charts you can do, but these are the basic ones. Okay, if you know these, then you're good. Okay.
What's the asterisks and circles mean on
That we will talk about it, right, later on. We consider these 18 and 19, these 2 dots or 8, these are extreme outliers, and these circles are mild outlier. When we make box plot, we can define some fences, help us determine whether this outlier is so extreme or not. Okay, and most of the software will also put marks, different marks for marking different type of outliers. Okay, we will learn that later on. Okay, at this point, just to let you know that we have something like this. Okay. Now, sometimes you have data that related to time, and you can make time plots. This is a time plot example. I have crime rates for different years, 95, 96, 97, 98, and so forth. And you want to display this information, I think you all can do that, right? You make a rectangular coordinate system. Usually, horizontal line you use at the time. Okay, okay, and mark 95, 96, 97, and then start plotting, vertical axis is the rate, start plotting these numbers, right? Usually when we talk about crime rate, crime rate is the rate, number of incidents per 100,000 people in the population, okay? So here you see a trend. Sometimes people connect these dots through a line to get a so-called line chart, right, for studying the time, sometimes we call it time series, right? The trend according to time. It seems like the rate is declining, crime rate, right? But this year, 98 jumped a little bit. Maybe there's something happened that year, and then it's steady going down. Okay, this should be pretty easy to make, right? Okay. And this is Youngstown's homicide rate. I got this from a professor in criminal justice. Okay, and from the picture, you see immediately what's going on, right? 1969 until 1991, it's kind of steady up and down in this range. Up to 90, it actually went up. Okay, something happened. Okay, do you know what happened? Some people told me something with gun control or something. I don't know. Okay, but it's not because of me, right? I arrived in 93. Okay, so actually 93 seems like went down a little bit, right? But the graphs actually tell you a lot, right, immediately what's happening in history. Okay. Also, you have to be careful. Look at this one. This is a national homicide rate. Actually, much lower than Youngstown, right? Youngstown is like range about 30, and then, but it depends on where the statistics from. It's from this Youngstown area. There's so many townships around it, and they're doing not too bad. Okay, and so you have to think about it when you look at this crime rate, how they do it. Okay, and a lot of times this crime rate is number of incidents per 100,000. Right? If you're in New York, living in that Manhattan area, living in that small place, think about what the crime rate is, because they have higher population density, right? So that would thin out the crime rate, right? If there are 100 cases, we have just 15 cases. But if you do the crime rate, our rate is higher. Which place is more dangerous? You know it, right? When you know your statistics. Anyway, let's get back to this. National homicide rate is this. And you wonder, this scale here is from 0 to 100, right? And there's not much fluctuation, okay? So how about this one? This is exactly the same data, okay? But I actually use 0 to 12 as a vertical scale. It tends to exaggerate the difference, okay? So the crime rate steadily increased, right, up to 1972, and then somehow 84 dropped down and then go up, okay? Okay, so if you want to see whether there's a big increase from 1964 to 72, wow, there's a big increase, very steep. But if you look back to the chart, it's not, okay? So it depends on what you're selling. If you're president of a country, you say, the United States is doing so great, the crime rate is steady there, not much change, right? Then you use this. If you're the person who are asking for grant, right, maybe police chief, right, asking for grant, they probably would do this, okay? There's no lie in there. Nobody lying there, but whether you really know your chart, okay? And of course, when you do it, you want to at least do an honest job, right? You don't want to distort these information. They're really good. When you read a statistic, be careful on the scale they use here, right? Read the chart carefully. Don't read it from a distance and make your conclusion right there, okay? Some chart may be misleading, okay? They are correct, but may be misleading, right? So you have to be careful. This is a chart that company compare their sales, okay? And Time Magazine is so proud of themselves, I guess. And I guess the person who make this chart tried to just display the height, using the height to compare. But they enlarged this pen in two dimensions. So in fact, this pen, actually, the height of this is probably, this is probably half of that, maybe more than half of that. But if you look at the size of these two pens, this pen probably is 3 times as large as this one. Okay, that's a distortion. This kind of statistic is not really professional. Okay, you can have so many little pans with the same width, right, and stacked together, and so you indicate the height. That would be the better way to do it. Don't enlarge the picture in two-dimensional approach. That's misleading. That's not a good statistic. Okay. So anyway, this is a caution. When you're making your chart in the future, you can make the chart so fancy looking, but don't just destroy the information. Okay. This is another chart, bar chart. When you view it from a distance without looking at the scale, you know that there's a big difference in the gender distribution. They're much more male than female, right? So if you look at the company statistic in male and female, somebody maybe complain that, well, you hire too many men than women, okay? But look at this vertical axis. This is from 210 to 270, okay? If I use 0 as a reference point here, now the difference is not that big. But if you view from a distance, didn't read the scale, then you'll be misled to something else. Okay, so be careful when you're reading any of these charts. Of course, when you're making a chart, right, you also want to do an honest one, right, and to avoid possible error. Okay.